I want to talk today about distillation. And distillation is a technique that's used to separate two or more liquids. A lot of times we say it depends on differences in boiling points, but it's really more accurate to say it depends on differences in vapor pressure of the liquids. We're going to talk about two different kinds of distillation, a simple distillation and a fractional distillation. And just to understand sort of what we're doing and what the distillation setup looks like and what's happening, this is an example of a simple distillation apparatus. So we have a mixture of the liquids that we want to separate right here, and we apply heat here to boil them. The vapor climbs up here and it touches the thermometer so that we can measure the temperature. Then it reaches this region over here, which is the condenser, this long piece of glassware. In the condenser, we're putting cold water in and it flows out to the sink. Sometimes it's recirculated, but usually water in and then water out to waste. And this cold water cools our vapor that we made by heating it back to liquid. And the liquid, you can see this is slanted, it drips down into our product collection flask. Sort of the super simplistic view of distillation is that when you have a mixture of, say, two liquids, the lower boiling liquid is distilled off completely first when we reach its boiling point. Then as we raise the temperature, the higher boiling liquids come off after the lower boiling liquids finish. Like I said, that's super simplistic and it's actually wrong. That's not how distillation works. There's actually a much more complicated picture that goes on, and I want to talk about that more complicated picture. The first thing we need to remember is what our definition of boiling point is, our boiling temperature. It's the temperature where our atmospheric pressure, whatever the pressure of our atmosphere is equal to the vapor pressure of our liquids. And that's where things get complicated because our vapor pressure isn't simply from one liquid when we have a mixture, but it's a mixture. It's all of our liquids are providing vapor and vapor pressure, and the vapor pressure total is equal to the vapor pressure of all of our liquids. I've just listed three here, liquid A, liquid B, and liquid C. And they each contribute an amount equal to the mole fraction. So to calculate the total vapor pressure, mole fraction A times vapor pressure A, mole fraction B times vapor pressure of B, and so on. So we have to account for the vapor pressure of each of our liquids and the mole fraction that they exist in. And that makes it more complicated than our simplistic sense. If I'm trying to purify ethanol from a mixture that's 20% ethanol and 80% water, my mole fractions of ethanol is 0.2 and my mole fraction of water is 0.8. So when I go to try to figure out what temperature this will boil at and what the composition of the vapor will be, this is what I'm looking at. The mixture will boil at about 94 degrees. Because at 94 degrees, the vapor pressure of ethanol is 1369 torr. The vapor pressure of water is 611 torr. I multiply my 0.2 mole fraction of ethanol times its vapor pressure and my 0.8 mole fraction of water times its vapor pressure, and I get 762 torr. 0.2 times 1369 gives me 274 for the partial pressure of ethanol. This times this gives me 49 for the partial pressure of water, and that adds up to 760 torr. And the boiling point, or the atmospheric pressure, is about 760. So this is what I have at 94 degrees. So if I think about my vapor mixture, this is my liquid. The vapor that forms above that liquid, if I want to know the composition of it, I have to look at the ratio of the partial pressures. So the composition of my vapor that goes up here and gets condensed and drips down into my product now is 274 over 762, or 36% ethanol. So I started with 20% ethanol, and I've enriched it somewhat to 36% ethanol. It's better, but it's certainly not 100% ethanol or pure ethanol like I would like. And what can we do about this? Well, we could take the vapor, the 36%, and do a second distillation. And when we did this second distillation, what we would find is the liquid boiled this time at 90.5 degrees. My partial pressure from the ethanol would be 434 torr. My partial pressure from water would be 342 torr. And the percent of ethanol in my mixture would be 56%. So again, it's better, but it's certainly not close to pure. So if I wanted, I could do a third distillation. Take the liquid, and when I did my third distillation, my vapor pressure of um, ethanol would be about 561 torr. It would boil at about 85.5 degrees, and now I'd be about 75% ethanol. And I could do this again and again. I did that on my fourth distillation. I would be 82% pure. The fifth one would be 88% pure, and so on. And actually, it wouldn't get much more pure than that after subsequent distillations because of something called an azeotropic effect, which we're not going to talk about today. But what I want you to realize is if we were doing these individual distillations over and over again, that would be a lot of work. By our fifth distillation to 88%, is there any way that we could sort of save the work of doing 5 individual distillations? And there is. We can use what's called a fractional distillation system. And I just want to show you what it looks like and how it works. You can see that our fractional distillation has some resemblance to the simple distillation. We have our liquids to be separated. We have the thermometer. We have this adapter. We have the condenser. We have the collection product. But we've got this fractionating column that's stuck in between the two. And this is the key to getting a good separation of our products or our mixture in a fractionating column or fractional distillation. Because what happens is instead of evaporating and going all the way up to the condenser in sort of one or a few steps, the liquid evaporates, then it hits this fractionating column, and there are plates in here or pieces of glass or something for the liquid to condense. So it evaporates and it condenses here and drips back down. And then it evaporates and condenses again. And it evaporates and condenses again. And as it works its way up the column. Well, every time the liquid condenses on one of these plates in the condensing column and in the fractionating column and re-evaporates, it acts like a tiny little micro distillation. So in our first, if you remember, our liquid starts off as 20% ethanol. Well, it evaporates and maybe it condenses right here. And when it condenses right here, that corresponds to our first distillation. And the liquid that condenses here evaporates again, and maybe it gets to right about this point right here. Corresponds to our quote-unquote second distillation. So now the liquid is 56% ethanol. Evaporation condensation cycle happens again, and now it's a 75%, and we keep repeating this like we did, so that by the time we reach our condenser, we've done multiple rounds of evaporations, and maybe our product is 88% pure now, or maybe even more on a long, this is a fairly long column, so probably get more than just these 5 cycles going on. But you get the idea. Every time it evaporates and condenses, we get purification of our liquids. We get enriched in the more volatile compound. Talking about fractional distillation, we're very much concerned about evaporation condensation cycles. It evaporates, condenses, evaporates, condenses, evaporates, condenses. It moves up the column. And if you're ever asked a question about a fractional distillation and its efficiency, you want to make sure you discuss the evaporation condensation cycles. In particular, the more cycles you have, the better separation you get. Well, how do we get more cycles? There are a couple things we can do. Longer column has more places for evaporation condensation cycles to happen, so you get more of them. The column tighter with more material, there are more places for the evaporation condensation cycles to happen, so you get more of them, you get better separation. The last thing that's not as obvious is that heating it slower allows for more evaporation condensation cycles to occur. So all of these things, longer column, tighter packing, heating it slower, gives you more evaporation and condensation cycles and gives you a better separation of your liquids. The thing to keep in mind is that all of these things, every time we do an evaporation condensation cycle, that takes time. What that equals is a slower distillation. It takes longer. So a lot of times you need to consider that. If you have two liquids that are very far away from one another in boiling point, that have a boiling point difference of more than 80 degrees, you don't need a lot of evaporation condensation cycles to separate them. So you might be able to use a simple distillation. If you use a fractional distillation, you might get a little bit better separation, but it's going to take a lot longer. So these are the things that we balance. How good a separation do we need versus how long it's going to take? And that's something you always consider when you're designing your experiment.